Başlıyor şimdi zaten ikinci ödevin konuları da.
Okay. Okay, let's get started. So as of last week, we finished discussing inter-process communication. Now, when you think of why do we need inter-process communication? Because you can see that, let's see, let me get my pen here.
Hocam RPC'leri görmedik sanırım.
Hı?
Remote Procedure Call var mıydı Interprocess Communication'da?
Okay. I don't, that's a good point. Let me see.
Şu soket de sanırım tam bitmedi de.
Soketten ama zaten network dersinde alacaksınız asıl şeyini, detaylarını.
Evet.
Yani yüzeysel. Ama RPC sanırım, evet Onur Hoca da bahsetmeli diye hatırlıyorum.
Ben Network OS'tan önce almış bulundum. Hani hiçbir şey yapmıyormuşuz ya Network'te, onu fark ettim.
Okay, let me just finish this off then. So Onur Hoca had discussed sockets, okay? And then as I said, there's a full course on this, so we will not be discussing this in detail. And so what I will focus on is basically these other issues, which is, you should be able to compare different IPC mechanisms, okay? So what we have seen so far is, like, we have seen a lot of different things, like, pipes, okay? Named pipes and, unnamed pipes and other things. And among all these different IPC mechanisms, one of the important things is this message boundary, okay? And when you work with, pipes and TCP sockets and etc., where we have basically a byte stream, then we have this issue that, since we are switching between different processes back and forth, and we have no idea when this switch will take place, when the client is, for example, is sending, hello, and how about an answer, then the server, like the listener part, can actually receive like hell or hello, how, and etc. Okay. So these are completely undeterministic, and just note that, you cannot, once you read something from the pipe, okay, then it's gone. So you cannot wait for the whole thing to be gone. You're just reading a stream of characters, okay? So one fix for this is you can just, limit the message length, which means that when you can read, remember that when you are reading, you can give, for example, the number of bytes from a stream, like, read FD, and then here's some maybe the address for, let's say the character, and then we have this N, which says, read this many characters. So this is a simple fix that you can use. And given all these discussions, we should also be able to discuss their performance and what are their, ups and downs. And usually, when you look at things, for example, pipe IO is the fastest of these IPC mechanisms, because, you're essentially just writing into an array in the kernel level. Okay, so it doesn't have too much of an overhead. When you look at, on the other hand, like message queues, they are slower, because you can see that there's a lot of synchronization is needing, because you're talking about these packages that are being queued, hence it has X more overhead. And among them, sockets, while they are slowest, but since they also support not only IPC, but also they allow different processes running on different machines to communicate. Like when you have a web server and a browser, then you're talking about sockets, which can reside on different basically machines. And but the nice thing about sockets is their portability. meaning that you can have different basically processes running and in them. And as a matter of fact, this portability and other things is so important. For example, in robotics, we are using something called a robot operating system, ROS. And in ROS, what that allows is we run a lot of different processes at the same time. Even if they are on the same machine, they open up sockets for each process, and we have this communication that goes in between. The nice thing is, for example, if you need more computation, you can then split the processes into two different machines and just point them to basically to these different machines, and they will still work fine. Okay, so that's a great thing for portability. Okay, and so here we have by different operating systems, all these things are like IPC support. This is a list of all of them. We have discussed pretty much all of them, like the semaphores, we'll discuss them later, okay? But all the other things are discussed. Now, the last thing that I will discuss is what's called a remote procedure call, or RPCs. Again, we will not get into the details of all this because all these things are basically deserve like there are big books discussions about this. So I will just introduce you what the idea is, okay? So an RPC is essentially a function call, and the difference is, the caller, that means that the client that you're making, and the process that's executing the instructions can be separate processes, and possibly they can even be running on different computers, okay? And there are a lot of different applications. For example, you may have a desktop server, okay, and it may be interacting with various components of a desktop, okay, and it can be running in different containers, or maybe sometimes we have a file system server that's providing file system services over the network, or a cluster of computers working in parallel, and etc. Now, what happens when you make an RPC? Well, when you have an RPC, you have to pass, remember, you're making a function call, right? And in this function call, you have to pass the calling arguments, and you have to pass this to the remote procedure. And so let's look at here. Here we have host A and host B. So host A is the caller, okay? And the other one is, if you wish, the client, okay? Or, well, I mean, client is not the proper thing, but whatever this function is doing. So you want to, for example, make a call, like, say here's int, and here's the argument that I want to pass. Then when you make this basic function call, there are a number of libraries, user space libraries, like some RPC, Corba. These are really, or MPI, these are really huge libraries, or SOAP here, okay? And what they do is they need to do some extra things so that you can call the function on another machine. And even the function that you call may be coded in a completely different language, okay? For example, your call here, like this can be your C++ code, okay? Whereas when we talk about this native function call that you execute, this can be, for example, MATLAB, okay? So this is all possible. What you do is you have this RPC library, and in this library, let me see if I have another thing. Okay, let's do this. Yes. So what you do is, there's this, the first part is marshalling, which means that, all these arguments should be passed, okay, to this library such that they can be sent over the network, okay? So this is, remember, when you're passing your arguments, this is programming language dependent, right? And what you want to do is you want to make them programming language independent, such that then you can then pass them over the network. And in a host, like here we have host B, then it's actually sits on, for example, on a particular circuit. It would accept requests. It doesn't do anything, okay? And when it receives it, it unmarshals or unpacks, which is essentially, converts the arguments of like what's the name of the function, what are the arguments, what are their types, and etc. So it unpacks and it passes this to this native function call, which then returns a value, okay? And these values are then again marshaled, okay? And the return value, whatever the type value, and you send the result, and on the host A, that you get the result, you unmarshal, and then your function then returns to the caller, okay? So this is the general idea. And this is the, like, you know, a detailed version of what I have told. What we actually have is, you know, when you have this, the client, which is like in this case, you know, process A, okay, it calls what we call the client stub. A stub is essentially, you know, this is like, you know, an empty placeholder. Instead of making a direct function call, you make a function call to the client stub, which is a placeholder, okay? And so this is a local procedure call, and you like, for example, as we have seen, your parameters may be pushed onto the stack in a normal way, and etc. And then in the client stub, this is where this is implemented by the library, and this is where the action happens. It packs these parameters into a message, okay, and then makes a system call to send the message. Remember, I'm sending them through a network, hence it requires a system call, okay? And so on the other hand, so this is where we have like, you know, this one is, this message is sent from the client machine to the server machine. So let me just come back here. So here we have, this is the server, because this is serving for this F function call, and this is the client, okay? And so when it gets them, then we have a server stub, which unpacks these parameters, which is called unmarshalling, and then it calls the server procedure, and then it does everything in the reverse direction, okay? So this is like, you know, I have some links here that you can like read like in general about all these IPC mechanisms. These are really classic books, so I suggest that you should, you know, go in there, and you know, there are a lot of details that you should be aware of. So spending time, if you have any free time, I know you don't have it now, but during the summer, etc., I highly suggest that you know, go through the exercises in these basically books. These are really nice. And these are some of the source code and demos. Well, I think Onur Hoca may have already discussed them. So this is basically, and all these resources are also available for the upcoming lectures as well. Do you have any questions so far? No? Okay, so then I can move on to our new topic.
Hocam RPC soket kullanıyor değil mi?
Hı?
RPC soket kullanarak şey yapıyor.
Yes, well, it depends on the library, RPC library. But I believe that they use sockets for most cases. Okay.
Bir alternatif değil yani. Onu sormak istedim.
So RPCs are essentially this is not an IPC in itself, okay, but this is like a library that provides some sort of like an extra level over this, okay. If there are no questions, then I want to move on to threads, which is again a major topic for this week. Now we have seen IPC. In the case of IPC, you remember that, you know, we have these. This is really slow. Let me see. Just give me a second so that I can. Print them, and then I can work on the PDF. For some reason, sometimes PowerPoint gets really slow.
Hocam, I thought it was me, but your voice is sometimes quite low. We can't really hear.
Okay. Is this good now?
Much better, hocam.
Okay, so I'll try to hold it like this. Stop sharing. Okay, let's open source. Okay. Any questions so far? So we have discussed IPC, right? Like in the case of IPC, it's really important. It's that, and the main reason is that when we have processes, the processes that we have, they actually live in completely separate worlds, right? They are disconnected, okay? There is process 1, and here is process 2. And in this case, we have seen how we can make them be aware of each other and communicate. And like, for example, in the case of a pipe, we say that there is a structure at the kernel level, so you can then read and write into this pipe, and that will be some that will allow us some communication. In the case of, for example, if you want to do things much faster, then we can have this shared memory, in which case, P1 and P2, these are and this area is the shared memory, which is basically appears in the virtual address spaces of both P1 and P2. And through this, then we can have communication between P1 and P2. Now, in all these things, it's nice. And the idea of having a process live in a completely isolated world is really nice for security and for basically protection of different processes running on the same machine. Okay, this is nice, but sometimes what you want to do is you want to have more better communication. Okay, and as I said, like we are talking about the concurrency, meaning that you want to do many things at once. Okay, for example, like think of the web browser. In the case of a web browser that you're using, you want to download a web page, and when you want to download a web page, then it means that you have to make socket connections. You have to wait for the data to come. You may be reading cache files. You should also be accepting user input. So all these things, and you have to do them in an interactive way, so that doing one of them should not block the other one. Okay. For example, like and how would you do all of them at once? Okay. Like for example, imagine your code to read from the browser, the URL, right? Now you want to check this, say whether the user has typed in something else, but at the same time, we should also be checking whether data arrived from the network that you asked for. At the same time, you want to refresh your display, right? So doing all these things at once is actually very tricky, especially when you have a single thread or execution. Or like when you have a web server, then what you want to do is you want to handle the incoming connections from multiple clients at once, multiple connections. Or sometimes you have scientific programs that may be processing different parts of data, and you want to execute them on different CPUs. Okay, and in each of these basic cases, you want to share memory across all these activities, right? In the case of a web browser, for example, when you want to download, the code that downloads data should basically, what if say you're downloading an image, okay? Then the other part of your program, which should be displaying them, this should be immediately visible, right? And all these things are very important. In the case of, for example, a web server, you may want to share the memory cache of recently accessed pages, or sometimes in the case of scientific programs, you want to just share one common memory and just let different processes being executed on these things. Now, can we simply do this with multiple processes? Well, yes, we can do that, but sometimes it becomes too cumbersome. And there are a number of basically reasons for this. The first one is, processes, they're not very efficient, okay? So we know that each process has its own PCB and operating system resources. But typically, when you look at for example, the PCB, like on Linux, this means that for each process you'll be holding something like 1.7 kilobytes of data. Okay, and this is large. And when you want to create a new process, this is expensive. Again, you have to have a new page table and etc. And in the case of like a process, we know that, once you have a process, they have their own address space. So by default, there is no sharing or there is no communication. Communication between processes is always an extra add-on that you have to do some extra works, okay? And this can be problematic when you want to have like a parallel concurrent programs that want to manipulate the same memory. For example, as I said, like this is your address space, like this is a place where, for example, you may be generating some images, downloading, or maybe, like you're doing some computer graphics, okay? Now this one, like there's also some part of your code that will be generating this, and another part is, for example, displaying. Let's say that another part is like I have another loop here that wants to access this and then displays this on the screen, okay? So this is a case where we need to have a lot of basically by default communication. Now, forget about this, okay. So what we want to do is, if you want to do like there are in a lot of these cases, you want to have sharing coming as a default capability rather than an exception, okay? And for most of the case, what you want to do is you want to share basically like, like the same code. Imagine, for example, that you have, let's say that, you have your, let's say that different tabs, right? Okay. And this is, for example, say that this is the code that I have here that is, say, handling is for one particular tab of a browser, right? Now, when you open a new tab, well, the code for the new one should also be here, right? So you want to share the same code because there's no point in basically duplicating that. And sometimes you want to share the same data, okay? This can be the cache, this can be other things. You want to share the same privileges, you want to the same operating resources like files and sockets and etc. So these things are nice, but for each of them, then you want to do is you want to keep certain things private, meaning that, if I have a tab and like in this case, I will say that like this is, let's say that this is the part of my code. And if I, in this code part, okay, if I plot the trace of my execution in this basically code, like, you can see that like there's a single, I will display them as this, there's this control flow, okay? And for example, if I, in this case, if I have a, for example, loop, it can be like this. This can be going like this and coming back. So you can have this, this whole code running in here. And what you want to do is you may wish to run, for example, if this is the code for handling a particular tab, if I want to have a separate tab, then I want to execute the same thing, okay? The same code, okay? But it should be different because it will be displaying a different tab, okay? Now, so it will be, now again, let's go back, when you're writing your programs, it will be easy, for example, say that displaying the code on your say window, you can just have something that runs in a kind of more like, infinite loop that will constantly update the display based on the images that you have downloaded and et cetera, okay? So it's easy to implement this. But then there's other parts, like maybe there's another part which checks the user input from the GUI, whether the user pressed stop, whether, he entered a new URL, okay? So this is, again, you can handle this as a separate basically loop, etc. Or there can be another part of the code where, you want your code to, say, send a request somewhere on the web, okay? And then over the network, and then wait for it, and it can remain blocked until the data arrives, okay? So when you want to do all these things in one single loop, then you have a problem, because either you have to merge all these different tasks in the same code, or and in any case, the code will get ugly, right? For example, you want to be both responsive, say to your user input, but you also have this piece of network code which may block because when the data that you have asked for hasn't arrived yet. Okay, so this is a problem, and it will be ideal. You want to have like multiple threads of execution running in the same space. So what we will define is we'll define an execution state, which is the CPU registers, stack, and program counter. And then if we can separate this, then we can have a separate thread. So the key idea of this lecture is that we want to first separate the concept of a process, which we know, okay, from a thread of control. And I will discuss what this is later. And note that the process is the address space and operating resources, whereas the thread has its own CPU state. So remember that when I was talking about the process, we had this PCB, right? And in this PCB, we had 3 components. And these were CPU state, okay, which is the registers, including your, say, program counter. And we had the address space, okay? And then we have the operating system resources, okay? So we have these 3 components. Now what I want to do is, with the address space, again, there are 2 parts. Like there is one part which is the regular, like global variables, code, and etc. So there's this, code, variables, heap, and etc. And there's also the stack, okay? And you remember that stack is where we keep track of very well as we make function calls and etc. And in this case, what we want to do is we want to separate the address space and code portion of this, and then use the CPU state plus the stack as the basically as the state of a thread. So let me move on, and things will become much clearer. So what we want to do is, we like this idea of multiple processes, because then you can have multiple things running at the same time. Now this is like, you have this code, and you have this, like, this guy here, okay? And he's basically executing a set of instructions. Now let's say that this is the code, and if you just plot the addresses of this guy, this will looks like a thread. And thread, well, in Turkish, it says, in Turkish, it's makara or iplik, okay? So this is a thread of execution. This is just like the line, the trace of your, the trace of the instructions that you have been executing, okay? So you want to have basically different active threads in the same address space in that. And what we want to do is, and with each of these threads, then we need to have that they should have their own CPU registers. Because eventually what we want is, if I have these 2 threads, this is like, imagine that in the case of a process, okay, so this is your process. In the case of a process, this is like, one person living in the house all by himself, okay? He's the only one that can update anything in the house, okay? He's not sharing anything with any other people, okay? And when you have multiple, as I said, this is basically what happens. In the case of a thread, the view is slightly different. In this case, what we want to do is we want to have multiple, basically, guys, okay, sharing the very same apartment, okay? So they will be using the same kitchen, they'll be using the same, bathroom, and etc. Okay? And note that these 2 guys, if you have just a single CPU, they will not be active simultaneously. So when this first guy is active, okay, then he will basically live in this apartment, and then we stop him, and then we can then execute the second guy, and then he will again, do things on itself. So they may not even be aware of each other, okay? So this, but with this case, it will be nice because you can now tell this guy that, well, your job is, to do the cooking. And for this guy, you know, you have a simple thing. You said you have to wash the dishes, okay? And so you can have like a different guy for each task, and they will just mind their own. And this will make your life much easier because in the if you want to do them with a single process here, then you have to do a lot of bookkeeping that, you know, you have to first, you know, wash the dishes and then cook and then do this and so on. It's actually messy. It will be much easier for you to basically have these separate threads of execution running this. So what do we need for this? Well, so we need to, but for these guys, we need to maintain some state. The first thing is the CPU registers, right? So we need to, each of these will have their own register value set so that when I switch from one thread to another one, then, you know, they should be you know, they have to, well, they maintain their own. And the second thing is they need to have their own stack, okay? And stack is important because they will, like each of these threads here, they will be making some function calls, and so they may go do recursion, etc. So we cannot use one stack to support all of them. They should have their own stack for this, okay? Now, the nice thing about this is, you know, communication between these threads is easy because we are sharing the very same address space. So here's a, you know, data, okay? And in this data, this thread can update it here, and then this thread can read it. Okay? So it will be immediately accessible, okay? So this is very nice. So what we will do is, you know, before in our discussion, we have been saying that, you know, the process was the unit of execution. That means that we were switching between different processes to give the illusion that multiple processes are concurrently active. Now, what we will do is we want to now use thread as the unit of CPU scheduling, okay? And that, you know, the process is just a container for multiple threads. And when you talk about the thread, it's not by itself sufficient, but it is basically related with a process that contains it, because the process portion contains the address space and the operating system resources. So in the single thread, like, you know, all the programs that you have written so far are single thread processes. Like, let's say that this is, you know, single thread. Okay. In a single thread process, you just have one basically thread of execution, which is what you've been doing. And in this case, you know, this is the address space. And you remember that, you know, like this is the roughly like starts from 00 to FFF, whatever it is. And in here, this is just roughly to, this is not like, you know, here's the code part. And our program counter or RIP points to somewhere in here, okay? And then we'll have like, you know, initialized variables. This is like our uninitialized variables, heap. And then we also have a stack where we have a stack pointer. So this is how this execution goes. And with this program counter, then we have like we run our things. And when you, as I said, with this program counter, if you look at how it moves in this, like you can see that it can be moving here. So this is what we call a thread. Now, if I want to have multi-threaded, basically multi-thread process, in this case, well, all these things will be the same. We'll be executing, we'll have access to the very same code, the same global variables here, the same heap, and etc. But we will have separate PCs for different threads. And this is like this PC, this is just an example. This is, but you know that this means that we have separate CPU states, okay? Because they just switch from one thread to another one, then you have to save and restore them. And moreover, then for each of these threads, we should have a separate thread. So separate stack. So this can be, this is the stack pointer for thread 0. This is the stack for thread 1 and thread 2 and etc. So this is, you know, really nice that you have this, you know, all these threads that are in the single process. You share all these things are by default, they are shared, okay, which is nice, okay? But we don't share, what we do not share, okay? Let's see, this here is not shared, okay? What we do not share is the CPU state, okay, which is registers including PC and the stack pointer, etc., and also the stack portion. Okay. And so this is like along this, note that plus what we also share is that we write this here, plus the operating system resources, it's also shared. Okay. So how do we implement threads?
Hocam,
Mhm.
what do we mean by operating system resources in general?
These are like open files. We have seen this, right? The open files, the sockets. These are all
Okay.
operating system resources. Remember, all those data structures that are maintained at the kernel level is not part of the process. They are stored by the kernel, and that's what we call as operating system resources.
Okay. Okay.
Okay, good. So what we do, like, to implement this, we break the PCB into two pieces, okay? The thread-specific stuff, which includes the processor state. Note that this is also implicitly basically points like since we also have this, stack pointer, okay? Then it also includes that. And there's this process-specific stuff, which is the address space and the operating system resource, like open files, sockets, and etc. So now we'll have like, we say this is a two-threaded program where we have like two threads here. And for each of them, like we have TCB, thread control block, okay? And then we'll have the PCB now doesn't contain the CPU. So now this PC that I talk about, it doesn't have the CPU state in it. Okay, it just has the other things like address space, open files, network sockets, and so on. So when I have like multiple threads, like here's I have a second thread, then it will have a separate CPU state, but you just point it to the PCB that it belongs. So they both share the very same address space plus the operating system resources. So now I note that the TCPs because of this is smaller, and hence switching between threads of within the same process is actually cheaper. Like in Linux, or like the thread struct has only, for example, 24 fields, whereas the PCB task struct has 106 fields. Hence, that's basically smaller. So what we do is, like we said that like for concurrency, we had this ready list, right? Or ready queue. And in this order, we have like queue for IO and etc. Now, instead of using the PCBs as the main basically unit, now we'll be using TCBs, okay? So for example, my ready queue can be saying that, here's the process, it's thread 0, okay? And here maybe another process, and here's the thread 2, okay? So with this, now note that if I'm switching between two threads in the same process, then I don't have to save and restore the address space, okay? Because they will be sharing the very same address space. But if I'm making a context switch between two threads that are in different processes, then yes, you have to change the address space. Maybe you should be invalidating the cache, and etc. We'll be talking more about this in the virtual memory basically discussion towards the end of the course. So with this, to threads, it's because like you can implement threads at two different levels: at the user level implementation, or the kernel level implementation. And as a matter of fact, in the early days, in the early Unix designs, the threads were not supported at the kernel level. Okay, and so the operating system, like it would just use processes with separate address spaces, but within the same process, then we could still have some multiple threads that are being active. Okay, so basically we can have these threads, like these user level threads means we have a user level library in which we can implement these multiple control flow threads, okay? And with operating system actually not being aware of the thread support. Now, how is this possible? You may say that, well, hold on a second, this is very difficult. Well, just remember that, when we have like all the threads that we have in a process, they share the very same address space, okay? So it means that when I want to switch from one process to another one, all I have to do is switch the CPU state from basically between these different threads, okay? And this, you can actually do this at the user level without any help from the operating system, okay? Now, this is how it used to be in the early days of Unix, where we did not have any kernel level threads. And so at the user level, as I said, later than kernel level threads became, but at the user level, all the thread functions were implemented as a user level library. Okay, and this is you'll be able to discussing Posix threads. Okay, as an example of this, and Onur will be doing some hands-on, basically exercises on this. So in this sense, the operating system thought that the process is just single-threaded, and it would just use the PCB and etc. And he didn't know anything about the multiple threads. But how do we then, implement, multiple threads at the user level? Well, we have in this the thread library, it would maintain a TCB for each thread in the application in the form of a linked list or some other data structure. And then it would allocate a separate thread for each thread, usually using malloc, okay? So this is basically how a user level thread library would implement basically multi-thread support. It would allocate its space, like for example, for the original threads that we have a stack. This is allocated, but this is provided by the operating system. But when you create a second thread, then this user level library would allocate this from the heap, okay, using malloc, and then let the second thread use this area as its stack. And you have to know that this should be allocated carefully and managed by this thread library. Now, how do we make a context switch? Meaning that when I say context switch, this is context switching between the same threads, between the threads of the same process, okay? So this requires that we need to swap the CPU state. Remember, for each thread, I have a different CPU state. But this does not require any privilege instructions because, at the level of the registers, you already can read and write, okay? So this means that, there is no privilege instructions are needed because all you have to do is save the contents of this register to some data structure and then restore it. Now, why is it safe to let the user switch the CPU state? Well, it's because, you already have access to the registers at any time. So there is nothing magical about it. So what I will discuss is, there's a set of actual C standard library routines for saving and restoring the processor state, okay? So these are called set jump and long jump. Remember, like all these, like there's nothing magical about it. The only part that's tricky is, when you're writing these libraries, you have to be a little bit careful. These are probably coded at the level of, at the assembly level because you cannot let a compiler do this, okay? So here we have these two functions that are implemented in the C standard library. The first one is set jump. This is actually, save the CPU state, okay, if you wish. So it saves the CPU state into this structure, into the jump buff structure, into this argument, okay? And then it returns. And then we have long jump. This is restore CPU state, okay? And it will take the saved CPU state, okay? And then restores it, okay? We also have a second value, which is this return value, okay? But we'll discuss this in a later. And then, you know, and there's this jump off structure, which essentially has the CPU specific fields for saving registers, and etc. Okay, so let's discuss this, and I will then let you go for the break. So this is an example that we have here. So here we have our loop. Okay, so we define basically the jump off as saved. Okay, so this loop runs from I equals 0 to 10, and it's printing its value. And then if it's I equals 5, then it says, okay, let me save the state. So it makes a call to set jump save. So at this, when you call this, then it saves the state into this saved data structure. And then it prints this, okay? And then we have this break, which means that it now jumps, it exits the for loop, okay? And it comes here. And then here we have like the restored, it was set to 0. The first time that we arrive here, so it's now 1. Then it makes this call, long jump saved. Now, what does it do? Well, it restores the CPU state to the one that's saved here, okay? Now note that, you know, when you save that, you have like your PC here, okay, was pointing to this line. Okay, and when you do a long jump save, now all of a sudden your PC was executing here, and after this, now your PC will again find itself right at this point. Okay, can you see that? Any questions on this? So and then it will find itself here, just returning from the set jump. This is like, and so at this point, you can see that there is some confusion. So when you return from a set jump, okay, then you have two possibilities. The first possibility is you've just called the set jump, you saved your state and you returned, okay. The second possibility is you return from set jump because it was called by a long jump, okay. Remember, like when you return from a long jump or a set jump, you will both find yourself here at this very point, okay? And you have no idea basically where you returned from. Maybe you returned from set jump or maybe returned from long jump, okay? And this is a major problem. And like in this case, you know, if I had returned this, then it would return 0, then you would have this infinite loop in here, okay? You'll be going back. Now, in order to break this with the long jump, we also have a second parameter, which is called return value. Now, what this says is, this is like this return value. When you restore the state, you find yourself here, but this time it would return this return value, in this case 1. Okay, I can make this 42. Okay, it doesn't matter. So you will get your return value. And this is, remember, in this case, this will be, you know, the value that you restore for RAX, right? Okay. So with this, then I can check whether I have returned from a set jump or whether I have returned from a long jump. Okay. And so since this returns 1, then after returning from long jump, then I will find myself in this else part. And then I will print this restored CPU state, and then it will loop and print the other values like 6, 7, 8, 9, okay? And then, you know, at the end of this, it will set the restore to 1. And when it exits now, since restored is set to 1, then you no longer do a long jump and you exit, okay? So with this, then this is basically what the printout is. So here you run the first part of the loop. This is where you did a set jump, okay? And then we break from the loop. And here we did a long jump, okay? Which we find ourselves back to the set jump. And then we continue and then we exit, okay? So with this, let me break at this point, and so that you can, I suggest that you look at this code, and if you have any questions, then I'll take it at the beginning of the next lecture.
Hocam, don't forget to set jump before taking a break.
Okay, I will. Thank you.
I really hated these functions when I was a student. They're difficult to read. I mean, it's very counterintuitive to the normal code flow,
Yeah,
right?
the name is a bit, yeah.
Yeah. No, that's why I basically write, save CPU state and restore CPU state would be a much better, basically, thing. And that's why I wrote that.
Yes.
Hocam, when we are back, maybe not right now, I don't want to take anyone's break, but could you maybe make a comparison with this practice that wasn't very recommended when it was taught, go to and jump thing? We didn't have CPU state related stuff when we used it, I think, go to and jump. Maybe can you compare them when you're back, if they're relevant enough, of course?
Yes. I will discuss that. I have, in the upcoming slides, I have some discussions related with that. Okay? So
Okay,
let's have a 10-minute break. And then I'll come back after that. Okay, so let's continue. Do you have any questions on this? It's a bit, mind-boggling, kind of mind-twisting thing, but it will become clear, I hope. Okay. So, so this is something that's really interesting, and you can actually try and see, what are the things that we can do using this set jump and long jump, right? And here is like what you have to be careful is remember when you're making when you're doing the set jump and long jump, what you're doing is you're changing just you're saving and restoring the register values, okay? And the stack and all the address space remain the same. And hence you have to be very careful in the status of the stake, what would, and you should be aware, and then there are some pitfalls with this. So for example, let's call this example where we have like at the beginning, we do a set jump, okay? And then, so we save the state into this buffer, okay? And then after that, we make a call to P1, and then P1 basically calls P2, and then which then calls P3, okay? And in P3, say that there is some error, and then we decided, okay, let's go back and let's do a long jump to this buffer, except that at this time, I'll be returning with 1, okay? So when we have this, note that, in this case, like, in our main, we call P1, okay? So this is basically when we did a save or set jump, okay? This is where we were, okay? This is the state of the CPU where we had saved, and this is where my stack pointer of my state is pointing at, okay? And I saved it, and after that, then, we called P2. So then comes the P2's stack frame. And in P2, maybe it'll call, it's a recursive one, it calls itself again. So here's the second instance of P2. And then it calls P3, is wrong. So it calls it's twice, and then it calls P3, okay? So, and then here, then, we had this, like, again, this is the simplest case that, we decided to make a long jump, okay? When you do a long jump to env, which is what we had said before, all of a sudden, so this was our, where my stack frame was basically before the long jump. And after the long jump, then I'm back to here, okay? So all these things are essentially discarded. They are still in the memory, but at this time, I'm now back to P1, okay? Now, in this case, like, it works fine because I'm in P1, and P1 has a valid stack frame so that, when you return from, when you go on with execution of P1, then it will be okay because the stack frame is fine, okay? So this is a case where we have no problem. But then you have to be careful what this, like there are some pitfalls with this that it can cause big headaches. Now let's have the following case. Now in this case, we, after saving our state, our P2, well, P1 calls P2, okay? And then after P2, then it calls P3, okay? And in P2, let's say that we save our state in here. So when at the time of the set jump, okay, which I was pointing to this, and the P2's stake frame was here, okay? So I saved my stake with my, RSP is pointing to this location. And then after this, well, P2 ends, P2 exits here. So hence this is all discarded. And this is discarded after P2 returns. And then we start executing P3. So we now have a new stack frame with P3. We go on and let's say that when we were in P3, then we do a long jump. We try to restore it. Now, all of a sudden, we find itself, remember, my RSP was pointing to here. But when it was pointing to here, P2's stake frame was valid. Now, when I do a long jump, then all of a sudden, I will be pointing to the very same stake, like, the same location in the stack. But now it will no longer have P3's stake frame, but it will be the so it will, instead of P2, we will have now, it will be pointing to P3's stake frame. And this way cause a lot of trouble because, in the stack, we'll remember that we do a lot of things. We push, old register values, we allocate space for local variables, and etc. Okay. Hence, this is a case where doing a long jump will become problematic because now the stack is completely wrong. We jump to a place where the stack is no longer valid and it doesn't contain, hence you have no idea what will happen from now on. Okay, so this kind of this is answers to Taha's question where we have these go-tos, right? So in simple implementation, when you do a go-to, you're effectively just changing the RIP, the instruction pointer, to some other place. But you have no idea what the state of the stack should be at that point. Hence, that's why it can be dangerous. Of course, in the go-to case, if you can have an implementation where it will take care of the you cannot prepare the stack for this. So you have to be, again, this is a case where doing a go-to between large basically spaces like this is problematic. Okay, are you satisfied, Taha?
Yes, Hocam, thank you.
Okay. So this is, for example, a simple thing where we have we can write a program that would restart itself when you press Control-C. And now, here is what we do is this combines what you learned. We say that, for sig int, which is Control-C, we are want to install a handler like this, okay? And after doing this, then we do basically save the state of this here into buff, okay? And then, then we get into this loop. And in this, when we are in this loop, it will sleep and write processing. And when we press Control-C at any point, then we'll be jump back to this handler. And in this jump back, when you do a jump, then you'll be restoring, which is now you point yourself back to, not here, sorry, but back to here, okay? So this is a simple program which restarts itself when you Control-C it. So let's move on. Now the idea of a thread is really basically nice, and you can see how it would make your life basically easier, and we'll see examples of this. But then there's this this notion of preemption, okay? And preemption, this is let me write this here. When I was first taking operating systems course, when I heard this was something I had no idea. Okay, this is a word that came out of outer space. I had no idea what this was. Okay, so preemption is the following. Let me just tell this in one slot. Preemption is to forcefully take a resource from someone. Okay, what can it be? It can be, for example, imagine, say that, you are talking, right? And when you're talking, if I before finishing your say question, if I can preempt you, meaning that, okay, stop for a second. You stand up to ask some question, but you're taking 20 minutes so I can preempt you, okay? And then maybe let some other students, talk a bit, okay? This is what we call a preemption. And in this concept, in our current context, preemption is about the allocation of CPU, okay, to a thread or process, okay? Meaning that, when you preemption means to forcefully take the CPU from a thread and give it to someone else, okay? So we will have, like, as we said with the threads, there are two different implementations. There are preemptive ones and non-preemptive ones. And I will basically tell you what they do. In the case of non-preemptive, threads, okay, this used to be the case in the early thread libraries. When you let a thread run, remember, like, when you say this is my address space, and you say that, okay, this is a thread, and so this will be running, right? Now, when you let this run, the thread library restores its state, and it will continue to run, right? But there's another thread here. Now, and how can I switch from this one to the second thread? Well, when I just point my PC, okay, to the beginning of this, then it will continue forever. If it's a infinite while loop, okay, then it will continue, and you will never switch back to the second thread that I have here, okay? So this is a problem. And this is a case if once I let it's basically a thread run, if I have no way of stopping it, if I have no way of preempting it, then this is a non-preemptive setting. This is like, imagine, I'm the, operating system, okay? And the resource that I have is the time that I listen to you, okay, the floor that you can speak. So when I, like in the non-preemptive case, when I allocate the floor to you, okay, let's hear about you, like it sounds, and then you start speaking. If you continue forever, then I have no way of stopping you, okay? So this is problematic. So in the case of a non-preemptive case, then each thread must call back to the thread library, at regular periodically, okay, so that the thread library can decide to run other things. And this is done using yield, okay? Yield means, yol vash, okay, or, just, stop and let other go, okay? So what you do is in your threads here, for example, you're running a lot of things. And in here, you may say, okay, I'll call yield. Yield is a function call to the thread library. And this is, and when it makes this call, then the thread library would check on other threads, which may be basically waiting for execution, and then save the state of the current thread, okay? And then restore the state of a waiting thread, okay? So this is a case, this is the only way that I can have multiple threads running concurrently. Now, in the setting, if one of the threads fails to call the yield, okay, then it will continue to run, and so it will never make a call, and all the other threads will starve. They will never get the CPU, okay, and you will have a problem, okay. So here's, like, as I said, what happens in the case of yield? Well, this is pretty easy, okay. So when you call the yield, then you see, save CPU state, okay, for current thread, okay, and then pick another thread, and then restore its state, restore CPU state for this new thread, okay? That's it. There's nothing magical about it. But all threads should be cooperative, meaning that in all threads, you should be making these yield calls, because otherwise you will have this problem where one of the threads will continue to use the CPU while all the other threads will freeze. So in order, since this requires a lot of basically restraint on the programmer side, which we want to be the new ones, we want to have like preemption. Okay. In the case of a preemption, what we can do is the thread library, we can tell the operating system to send it a signal periodically. And we have, for example, the sig timer. Okay. The sig timer, you can say that, well, you know, it will generate, it will make this signal handler be called periodically. And then we will be jumping into the signal handler. And in the signal handler, then it can save the state of the current thread and switch to another one, right? Okay, so this is called preemption, because with this way, even a thread doesn't call the thread, it can still be preempted, okay? Preempted, and so we can forcefully to take the CPU from him and then basically give it to someone else. So in my example, you know, I am the operating system and I have this timer, okay? Say that when and then, you know, all the students are threads. And when you want to ask, if you need the CPU, then, you know, like then you're on my list. So I let you to speak, but I also have this timer and which runs at say, 1 minute. If at the end of 1 minute, you don't block, you don't go for IO, you don't give up the CPU, then I can say, okay, I will save your state, I will stop you, I will save your state, I will pick someone else, let him talk, and then, you know, like, you know, and go on, okay? So this is basically much more reliable and basically better for programming. So we said that, you know, the threads can be implemented at like 2 levels, like is it a user level, right? And the kernel level. And you can implement them at the user level, and but there's also you can also have this implemented in kernel level, which is the case nowadays in all modern operating systems. Now, the nice thing is implementing the kernel level threads is that the operating system now knows about all the threads in a process, okay? So in its ready queue, okay, in its ready queue, then it will have, you know, say thread 1, thread 2, and etc. Okay, this is nice. So you can switch back and forth between them. That's the advantage. And the negative part is that, you know, when you want to make a thread operations, like, you know, switch to another one, yield, or, you know, insert a new thread and etc. Now, this means that we need to make a system call to kernel, okay? So in order to create, destroy, or context switching, they will all require system calls, and this is usually more expensive. So to compare them, these user level threads and, you know, kernel level threads, for the user levels, the pro is that, you know, the thread operations are really fast because you're making a, you know, local function call in the user space. It can be, you know, 10 to 100 times faster, okay? And also the thread state can be very small, okay, just the CPU state and plus stack, then there's no additional overhead. The downside, however, is the following. If a thread blocks, then it stalls the entire process. What I mean by this is the following. In the early days, when we did not have kernel level thread support, we had this user level threads. And so we had these browsers, okay? In the browser, you know, they would implement these different components of the browser with different threads. So there's one thread for the GUI, okay, which handles, you know, pressing the buttons. And there's another one, for example, say displaying the, you know, the tabs, okay? And which again makes connections over the network and then waits for it to come and etc. So usually they would both run fine, okay? But then what happens, well, like when you're in a tab, you try to open an invalid URL, okay? So then you switch, so you make a switch to this tab thread. You execute this, but then, you know, it goes for IO. For example, it says, okay, I'm waiting for data from network, so I will block, okay? So this would block the tab. And when it blocks, then, well, from the operating system point of view, well, the whole process is blocked because it's waiting for data that's incoming from the network, right? So it will block it. And then now your thread library, you cannot run your thread library because, well, the operating system is no longer running you. And at this time, your GUI, you try to click on your stop button in your, but you cannot press the stop button because the GUI thread is not running, okay? So this is what I mean by if one of the threads blocks goes for IO, then all the threads becomes basically blocked because the operating system is not aware that there are multiple threads alive in that one, okay? This is the first negative side. The second one is you cannot use multiple CPUs. I mean, nowadays you have dual cores, quad cores, etc., etc. Now, when you have a kernel level, when you don't have any kernel level support, then if this is your CPU 1 and say that CPU 2, then if you're running on the CPU, you will continue, all your threads will run on the same core. Okay, so you cannot split some of your threads to run on the second CPU, no matter how empty it is. But if the kernel knows is aware of the threads, which is the case in the case of a kernel library, then the thread 1 may be running on the CPU, and then the thread 2 may be running on the next one, okay, which will actually run faster. Okay, this is again nice. In the user level case, again, the operating system now is that it cannot make any good decisions. For example, since from its point of view, it doesn't have any idea what the threads are doing. Is it the GUI? Is it that's important, etc.? It's like from its point of view, all the threads are equal. It doesn't know what they're doing. And so it will then it can just for example, process with only idle threads, or it can deschedule a process with a thread that's basically holding it. Like we will learn more about this later. Don't worry if you don't get it the first time. So regarding the threads, we will now on Monday, Onroja will be discussing the Posix threads interface, okay, which is actually contains over 60 functions to manipulate threads from C programs, okay? And so I will leave this part to you. So this is the portion that we'll be discussing later through Onroja, okay? And let me just, I will skip this. And now let's discuss the threads versus processes once more, okay? So with processes, we know that the processes that forms a tree hierarchy because they are spawned by forking, okay? So like here's P0, P1, then you can have multiple shells and etc. Okay. In the case of threads, well, the threads basically are all equal, and each thread can kill another. This is like a lot of the discussion that we have is about these P threads or Posix threads. Okay. And each thread can wait for another thread to terminate. And what we call as the main thread is the first thread to run in a process. Okay. Now, with all this being said, then we arrive to a fundamental problem, which is called synchronization. Now, let's say that I have two threads, thread 0 and thread 1, and they are both accessing a variable called foo. Okay. Now, when one of them tries to write and update foo, and the other one is like trying to again update it, then its value can be problematic. It will not be synchronized. Okay, and this is called the synchronization problem, and I will now discuss this in the upcoming slides. So again, now we're on Posix threads. We have these really beautiful tutorials that are available on basically on the web. So I suggest that, and this will be, by the way, with the threads. It will be the main topic of your second assignment. Okay, so surprise, surprise. And so yeah, I'm pretty sure that you'll be, learning about them and looking at these tutorials when the time arrives. Okay. Do we have any questions about threads before I switch into synchronization? No.
Hocam benim bir sorum var.
Hı-hı.
User level threadlerle I/O blokunu handle edemiyor muyuz? Öyle bir şey gördüm de slaytlarda.
You mean in the user level? No. If you are using user level threads, then let's see. If you're using user level threads, if one of the threads go for I/O, okay, then this will block everybody in that process. All the threads will be blocked because from the operating system point of view, if anything goes for I/O, then it moves that process from the ready list and it puts into the wait list. Okay, hence it will remain there. So it's not aware that there are other threads that are executing because the operating system doesn't have any concept of a thread.
Yani they are not equal, like the user level threads, yani o şeyi yapamıyorum değil mi? Yani mesela bir I/O için beklerken arkada işlem yapma, aynı proseste işlem yapamıyorum yani. User level thread library'siyle
Yes,
bir tane.
exactly.
Yani onu yapmak için kernel şart. Yani kernel.
That's correct. Kernel level library. Kernel level library is required for this because remember, like, in your, for example, this is like, it's similar to this. For example, I see the whole class, like you're all individual, you have, say that, 88 students here, right? So instead of seeing 88 students in the same class, I may be seeing you just one big lump, okay, in which you're running. So for example, if anybody like makes cheats, okay, in his assignment, then from my point of view, the whole class is cheated. So I have two cases. Is there a cheating in this class or no cheating in this class, okay? I don't distinguish between individually, between Ege or Hüsna, but from my point of view, if any of you do that, then the whole class is on this, disciplinary committee. Okay?
Okay hocam.
Okay.
Hocam ama bu sorunu çözer sanırım değil mi? Sinyal, yani preemptive yaparsak. Sonuçta thread uyuyor olsa da sinyal geldiği zaman yani signal handler preempt edebilir uyuyan sistem.
Yes, not really, because like no, but the operating system, from operating system point of view, if anything goes for I/O, it moves this from the ready list. So it never tries to switch back to that process.
And even if it is signaled, it will switch to that process.
Because the signal handlers are run before the context switch to that process. Right? So when a thread in a process goes for I/O, it is removed from the ready list. Hence, the operating system never tries to make a context switch to run that. Okay?
And that's true.
And the signal handlers are run before you're making a context switch to that process.
Yes, but the signal handler could restore another user level thread. That's what I was trying to say.
Yes, but even that case, if you want to do that, then the operating system should try to make a context switch to that process, but it's not in the ready list yet. Okay? No, it's not clear.
Okay, I'm not convinced, hocam.
Well, it's like you have to remember the first thing is the signal handlers are executed before making a context switch to that process. Are we clear on this?
Yes, hocam.
So the signal handlers are not run asynchronously. The operating system runs the signal handler before the context switch.
So you're saying that as long as a process is waiting for I/O, it's never going to run a signal handler until
exactly.
I/O returns?
Exactly. Because it's not in the ready list.
But hocam, system calls sleeping I/O can be interrupted. In fact, sleeping I/O can be interrupted by signals.
You have to be a little bit careful. I would like.
But anyway, it's kind of a complicated thing, so
yes.
We can go on with the lecture. Sorry about that.
Okay, let's move on. Let's see. Okay, so this brings us to the one of the most important basically lectures of this whole course, which is called synchronization. Now, as we said, when we are talking about threads or processes that are accessing to the very same pipe and etc., then we are trying to access a shared state, a shared variable, okay? And this can be the multiple threads maybe accessing the same memory cache, etc. Or like sometimes you want to coordinate the execution of different threads. You want to, for example, when you press the stop button, okay, then you want this to cancel the download of the current page, okay. Hence, the GUI thread, which serves the stop button, should be able to kind of signal, and when I say signal, this is not the regular signal says, but it should be kind of communication, okay? This is not the regular signal, to download to the download thread, okay? So for this, we need to control this cooperation and make sure that these threads, even if we interleave their executions arbitrarily, because you have no control over which thread is running at which time and when would it be stopped and we switch to another one, etc. So basically, the switch is the cooperation, basically the switching between different processes is actually not under control. This is called actually scheduling, and we will see that this is something that's not that we have to handle. Okay, so we will be looking at shared resources. What do we mean by this? Okay, the first thing is like what we say is a shared resource. It can be a shared variable. Okay, and this shared variable, now remember that like in the case of our, for example, multi-threads, so this is my address space, okay? And in this case, when we talk about, for example, global variable, okay? In the global variable, now that's a shared resource, okay? Because all threads can access, read or write, okay? And or like, heap, that's also a shared resource. What's not shared is, for example, or like, for example, stack, okay? Stack is not a shared resource, okay? And also, like, what do we have in stack? Local variables, okay? So local variables that we have, which are stored in the stack, are actually not shared resources, okay? So when I'm talking about shared resources, I'm mainly talking about these global variables that are basically in the address space. And we will see that, if we have multiple threads, okay, that are reading, modifying, or writing a shared variable, then we can have some unexpected results. And we will see first what these problems are, okay? But then, and then we will move on how to control access to these shared resources. So we'll be discussing about locks or some higher level mechanisms like mutexes, semaphores, monitors, and condition variables. And as we study them, we will also talk about some patterns for coordinating access to shared resources. And this is, as we will see later, writing a multi-threaded program can be actually very daunting, a very complex thing, because each time you run, you may get a completely different result. So let's have an example before we move on. Now, let's say that, we have like these, we implement a function to withdraw money from a bank account, and we have all these ATMs. We have a lot of different ATMs that are allocated, right? And from each of these ATMs, then you have access to your, for example, account, which is a shared variable in the memory, okay? And typically on each of these ATMs, which you can see that as a thread, okay, a separate thread, then you can execute the withdraw function, saying that, okay, this is the account, and I want to withdraw this much money amount. And this requires that, will at least 3 instructions, and which I have written in terms of a function, but, I will give you an example why you cannot do this in less than 3 instructions. The first thing is get balance from your account. This returns you how much money you have in your account. And then you deduct it from your basic balance, whatever you want to withdraw, and then write it back into the memory, and then return this, okay? So this is the withdraw function, and the withdraw can be executed here, or here, or here, okay? Now, suppose that, like you and your friend, you have a bank card, okay, accessing the very same bank account, which can happen, and you have, say, 1,000 liras. And you both go to separate ATM machines, and you want to withdraw 100 lira from your account, okay? So in this sense, like, at the computer, or at the server system, you're basically executing 2 different threads. Like, I'm putting them into, like, it's the same code, but different threads executing the very same thing. Now, what can happen? Like, what are the possible balance values after each thread runs? Now we can look at this. So as we run this, note that we can have, let's say that we have preemptive scheduling, which means that, when you're executing these withdraw functions, the operating system may stop one thread and switch to another thread, and then, run it a bit and then switch back to that, right? And this can happen at any time. We have no control. And so we have to worry about the worst case. So let's say that, we have this thread. So you read whatever amount that you have in your money, like account, say that this is, 100, and what you get, we have 1,000 lira, okay, as a result of this. And then we deduct it by our amount. So now this is 100. Now my balance is now 900, okay? And then at this time, we have a context switch, just pure luck, right? And now your friend's thread gets to run. Now, he again gets the account, okay? Remember, it's reading this account from the memory, right? And it will still read the 1,000 here, okay? Because although it's updated, now this balance is still in the register. It's not in the memory. It's not written back. And then it deducts 100, so it gets basically 900 here. And then it updates the account. Now, in this case, it basically updates the account with this new balance, which is 900. And now we switch back to our first thread, and it then executes the put balance, and now it updates it with 900, okay? So obviously, who is happier? Well, you are happier because you have withdrawn 200 liras, but the update was made for 100 liras, right? So this is what we call a problem that we have in here. Now, let me just show you basically what this means in a much simpler case, okay? And you can see how it works. So this is a case where like we have this basic function, and I will just skip that. This is where we create a thread. Okay, you will learn more about this in Onur Hoca's lecture on Monday. So you basically create a thread, okay, with this count. Okay, this is where one thread runs. Okay, and then we create another thread, TID2, with the same, running the same routine. Okay, and in this routine, what we do is we have a we have basically a global variable. This is our shared resource, shared variable, okay? And both of these threads now loop and update this variable, okay, in this loop, and then returns. That's it. So don't worry about this. This is all. And then at the end of this, all these threads return, and then you print basically the results, okay? And what you want to do is now, like in this case, you can see that I have two threads, okay? And these two threads, let's, how much is it? This is like, say, they are both incrementing the count by 100 million, okay? Since I'm running the threads twice, what do I expect to see? Well, I expect to see the final value of this count be twice of this 100 million, which should be 200 million, right? Because I have these two threads, they are both reading and writing and updating that. And when you run this simple example, you run this once, again, you get this result, which is wrong, okay? This is like 198 million, etc. You run it again, you get a different value, and which is still wrong, okay? You run it again, you get another wrong one, and so what you see is we have two problems. The first thing is, well, the count should have been equal to 200 million. First, we're getting the wrong result, and second, even more important, at each run, we are getting a different result, okay? On computers are supposed to be reliable. When you run it, if you have a bug, you are supposed to get the very same result. It may be wrong, but it should also do the same. But this is a case where this is like crazy. This will drive you crazy because each time you're getting a simple thing, and you cannot even reproduce the same thing, okay, unless you're. Now, what's happening here? Now look at this code, okay? This is where we are updating this count variable, okay? And when you look at this code, this is the body of this code. And so I'm trying to update this count by one. And you can see that this requires like 3 instructions. The first one is I read count from memory into my register. So let me say that this is your memory, and this is the count, okay? And then now this is my register, okay? And I have, now here's my EAX, okay? So an update requires 3 operations. The first one is you copy this into your register, okay? The second one is, which is this, it's implemented as LEAL, but this is effectively incrementing by 1, okay? And then the third one is now move this back into the memory, okay? So any update requires these 3 instructions at minimum, right? Now, what happens? Now, let's see that, what happens is the following. Let me go through this example. So here's my register, and let's say that I have this count. Let's say that this is like its initial value is 5, okay? And now remember that for each of my threads, I have they have their own CPU state, right? Okay, they have their own registers. So let's say that this is my T1 register, and this is my T2 register. I have the same basically thing here. And I will be running these load, update, and store sequences in each order. So when I do a load, okay, I load it into my register, okay, now it's 5. Then I increment it to 6, okay, I increment it into 6, and then after that I have a context switch. Now I switch to T2. Now with T2, then I do the same thing. I load it to my register as 5, okay? I increment it to 6, okay? And then after that, I write it back to my memory, into my memory. Now it also becomes 6, okay? Then I switch back to T1. Now in T1, what's left is then I write it back onto my basically memory, and again I overwrite 6 again, okay? So you can see that what I have shown in my ATM example is a fundamental problem here, because the main reason is, you know, here in these CPU states, I am duplicating a variable's content, okay? That's why I have a problem. Like I cannot update a variable in the memory in place, okay? And hence we are having this problem, and you know, it's not a matter of like implementing a function. This is with this kind of, you know, processes, we will have this problem, okay? Now this problem is called a race condition, okay? A race condition, we call it a race, is that, you know, the correctness of a program depends on one thread reaching a point X before the other thread is reaching a point Y, okay? Now, and this regards synchronization, it's because depending on the position of the context switch, okay, then we will have a problem with this. So I will stop here and I will open your poll, okay, so that we can then end after this. Okay, here's your poll, and you have, say, 3 minutes.